And in this session, we are going to talk about the decimal representation of real numbers. So over here, first we are going to do the decimal representation of rational numbers. So there can be two types of decimal representation of rational numbers. The first can be terminating decimal representation. What does it mean? Terminating means it is stopping after some places of decimal. So this is the first type. Now the second type of decimal representation can be non-terminating but repeating. So whenever the remainder does not become 0, the decimal representation will be non-terminating but repeating, or we call it recurring decimal representation because it is reoccurring after some places of decimal. So every time you will not get numbers whose decimal representation will terminate or non-terminate but repeat. There are numbers in which the decimal representation is neither terminating nor repeating. Hello everybody, welcome to the live session by Infinity learned by Sri Chaitanya. I am Misbah, your maths educator, and in this session we are going to talk about the decimal representation of real numbers, that is rational as well as irrational numbers. So let's start with it, guys. So over here, first we are going to do the decimal representation of rational numbers. So there can be two types of decimal representation of rational numbers. The first can be terminating decimal representation. What does it mean? For example, I have got 7 and I am dividing it by 5. What will you get? So you see over here 1.4. So this is a terminating decimal representation. Why we are getting a terminating decimal representation? Because over here the remainder becomes 0. It means if you divide 7 by 5 over here, what are you going to get? So you see over here, you'll put a decimal and then you will put a decimal, then you'll get 5 4s are 20 over here. That is 0. The remainder is 0. So when the remainder becomes 0, it is a terminating decimal representation. It means it is stopping after some places of decimal. So it can be like this, for example, 15.125. It can be like this, 6.123. Obviously, these will be the decimal representation of such big numbers. So obviously, I cannot show the division over here. I hope you understand. So these are terminating decimal representation. Terminating means it is stopping after some places of decimal. So this is the first type where the decimal representation is terminating. I hope this thing is clear to you. Now the second type of decimal representation can be non-terminating but repeating. For example, in the same case, if I take 7 divided by 3. So if you actually divide 7 by 3, what will happen, guys? You see 3 2s are 6, remainder is 1. And then if you will put decimal, then you will get, you see 3 3s are 9, remainder is 1. Again you will put 0, 3 3s are 9 and again remainder is 1. So you see it will keep on going. You will never get remainder to be equal to 0. So basically, the decimal representation over here is of this form, 2.333 and so on. So this is non-terminating but repeating decimal representation. So the part of the decimal which is repeating over here, we write it like this, 2.3, and we put a bar over that thing which is repeating. And this bar is not called a bar actually, it is called vinculum. It is called a vinculum. I hope this thing is clear. So whenever the remainder does not become 0, the decimal representation will be non-terminating but repeating, or we call it recurring decimal representation because it is reoccurring after some places of decimal. Okay. And one more thing, for example, I have got 15.123 and we are putting a bar over it. Something like this, it is happening. So over here you see 1, 2, 3, that is called the period. That is called period. The string of numbers which is repeating, that is called the period. And over here 3 digits are repeating. You see 3 digits are repeating. So 3 is called the periodicity. It is called periodicity, or you may call it length of period or length of period. I hope this thing is clear, guys. So again I am repeating, two types of decimal representation of rational numbers are possible. Whether it can be non-terminating but repeating decimal representation, or we call it recurring decimal representation, or which we have seen in the previous slide, it can be terminating decimal representation, which is stopping after some places of decimal. So the two types of decimal representation are there. Now there is one more thing. How can we write a terminating decimal representation in the form of p by q, where p and q are integers and q is not equal to 0, because that is the definition of rational numbers, right? So if it is terminating, for example, I have got 156. So it is very easy to write it in the form of p by q. You just remove the decimal and you can write it like this. You have studied in earlier grades, right? And obviously you can simplify it. So you will get the simplified form of the rational number over here as well. I hope this thing is clear. But for example, you have got a non-terminating but repeating or recurring decimal representation. So that can also be asked to write in the form of p by q, where p and q are integers. So you have studied this thing in grade 9. So I'll explain it using one or two examples over here. For example, and I'll explain using the short trick. I'm not going into the actual process of that. For example, I've got 1.53 and vinculum over 3 is there. So what is the shortcut over here, guys? Write the complete number, that is 153 over here. Now subtract the number on which bar is not there. So you see on 15 bar is not there. Divided by, you see on one digit bar is there, or you can say vinculum is there. So 19 will come over here. Now on how many digits after the decimal bar is not there? On how many digits after the decimal bar is not there? One such digit is there. So you will write 10 over here. I hope this thing is clear. Now I can further simplify this. You can see 153 minus 15 will be what? That will be 138, right? That will be 138 divided by 90. And obviously you can further simplify. So you see, I think it is further simplifiable. So you see, this cannot be further simplified. So you can say that the p by q form of 1.53 and a vinculum over 3 is 23 upon 15. And this is the shortcut method which I have explained. That is, there is one actual method as well. It is there in grade 9. I hope this thing is clear. Let's move on, guys. So suppose I'll explain the same thing using one more question, and then we will do this question as well. One more question on the form of the recurring decimal representation in the form of p by q. One more question I'm explaining, okay? So for example, I have got 2.15326. Suppose I'm giving a big number. You will never get such a big number in the examination. Just to explain the shortcut thing to you. So what will you do? You see, vinculum is over 26. So the first thing is you'll write the complete number 215326. Write the complete number. Then subtract the number on which vinculum is not there. So that will be 2153 over here, right? Divided by, now on how many digits bar is there, or on how many digits vinculum is there. So two such digits are there. So you will write 2 9s over here. Correct? Now on how many digits after the decimal bar is not there? On how many digits after the decimal bar is not there? So 3 such digits are there, 1, 5 and 3. So you will put 3 times 0 over here. Obviously you have to simplify it further so as to get the p by q form. I hope this thing is clear. Obviously after here you can simplify, you will never get such a big question. This is just an example to explain the shortcut method to you. I hope this thing is clear to you. Now you see, this type of question is also asked. Which of the following rational number have terminating decimal representation? Now you know the terminating decimal representation and non-terminating decimal representation of rational numbers. Now for example, you have been given some numbers. How can you judge, how can you say that this number will have a terminating decimal representation and this will not have a terminating decimal representation without actual division? They are not asking to divide 16 by 225. It will take too much of time, right? In the same manner, they are not asking to divide these things. So there is a thing actually. See, I will explain that. So a rational number will have a terminating decimal representation. For example, I am writing P by Q. It will have a terminating decimal representation when the denominator is of the form 2 raised to the power m into 5 raised to the power n, where m and n are whole numbers over here. It means they can be 0 as well. M and n are whole numbers. It means they can start from 0, 1, 2, 3 and so on. But one thing is very important. First, you have to make sure that it is in the simplified form. Make sure that maximum simplification is done. Then only you can judge whether it will have a terminating decimal representation or non-terminating decimal representation. So first simplify, then you have to decide. Okay, I'm not going into the deep logics. This is a video for you to understand the concepts in short, right? So that you can take it as a quick revision. I hope it is okay. So, for example, we have this question, how can we decide whether it will have a terminating decimal representation or not? So, the first thing is you have to see if it is in the simplified form. You see 16 upon 225. First check that is there any common factor between the numerator and the denominator? Can it be further simplified? So, you see no common factor is there, right? So, now you can do the prime factorization of 225. What is 225 guys? 225 is 15 square only, right? 225 is 15 square. So, 15 square is nothing but 3 into 5 the whole square over here. I hope this is clear. So, you see this is nothing but 3 square into 5 square. I hope this thing is clear, right? So, you see this is not of the form 2 raised to the power m, 5 raised to the power n, and we have already checked that there is no common factor in the numerator as well as the denominator. I hope this thing is clear. So, you will say that this number will have a non-terminating recurring decimal representation. I am writing in short R, suppose. A non-terminating recurring decimal representation this will have. In the same manner, can we check for this? So, this is 5 upon 18. So, 5 upon 18. So, first see if there is any common thing in the numerator as well as the denominator. So, you see nothing is common and the denominator is what? 18. 18 is what? 9 2s are 18. So, 2 raised to the power 1 into 3 square. It is the prime factorization of the denominator. So, again this is not of the form 2 raised to the power m into 5 raised to the power n. So, it will again have a recurring decimal representation, or you can say non-terminating but repeating decimal representation. I hope this thing is clear. What about the third part over here, that is 2 upon 21. So, these are very simple examples, although 2 upon 21 if I take over here, you see 2 upon 21. So, 21 is nothing but 7 3s are 21 and no further simplification is possible in the numerator as well as the denominator. So, again the denominator is not of the form 2 raised to the power m and 5 raised to the power n. So, this will have a recurring decimal representation only. Now, what about the last part over here, 7 upon 250 if I take, 7 upon 250. Now, you see over here, no further simplification in the numerator as well as the denominator is possible. And if you do the prime factorization of this thing, 250 is nothing but, you can prime factorize it. You can think that it is 25 into 10, right? So, basically this is 5 square and this is 5 2s are 10. So, this will come out 2 raised to the power 1 into 5 cube only. I hope this is clear, right? 2 raised to the power 1 into 5 cube. So, you see this will have a terminating decimal representation because the prime factorization of the denominator is of the form 2 raised to the power m into 5 raised to the power n. I hope this thing is clear to every student watching this video. So, let's move on guys. So, many a times this question is also asked in this concept that if you find the decimal representation of this number, obviously you don't have to actually divide and check, right? Just by, I'll tell the method to you, you have to tell that after how many places of decimal will it terminate. Now, how do you decide the number of places of decimal, a number after which a number terminates. For example, you have got 125 or 123 divided by 100. So you know that division by 100 is very simple. 2 zeros are there. So you put a decimal from the right after 2 places. This you have been doing since childhood, right? So basically, if I've got the same number 123 and I'm dividing it by 1000, you will say that it is 0.123, correct? So you will say it's terminating after 3 places of decimal, it is terminating after 2 places of decimal. So in this manner you proceed, right? So basically, you want any power of 10 in the denominator. For example, this is 10 cube over here, right? This thing is 10 square over here. You want a power of 10 in the denominator so as to decide that after how many places of decimal will it terminate. And one more thing, first simplify, don't because sometimes it will happen that some common factor is there, so it can confuse you, right? So for example, this number is 327 and in the denominator you see this is 2 raised to power 3 into 5. So basically, in order to decide the number of places after which it will terminate, you want to try to make the number of tens in the denominator. That how many 10 can you make in the denominator and nothing else must be there in the denominator. You understand this logic? So basically, this is 2 raised to power 3 into 5. So you see, 10 is nothing but 5 into 2 or not? Tell me, it is 5 into 2. So basically, you want to get it exhausted because you cannot leave anything in the denominator, right? Because only power of 10 you want over here, right? So can I multiply by 2 square over here in the numerator as well as the denominator? Why I am doing this? Because after doing this, if you see the denominator, what is that, guys? This is nothing but 2 raised to the power oh wait, I did a small mistake in this thing. Wait, give me some seconds. So I want to make power of 10 over here, right? I want to make power of 10 over here. So 2 cube is there, 5 is there. So I want to multiply and divide by 5 square over here, right? Then only the denominator will be completely exhausted. I hope you understand that. Then only the denominator will be completely exhausted. Because the denominator will become 2 cube into 5 cube over here, right? 5 cube. So this can be written as 2 into 5 raised to the power 3 only. So this is nothing but 10 cube. You got that logic? So basically in the denominator you can make 10 cube and there is no other thing in the denominator. So 10 cube means divided by 1000. So you see, if we were dividing by 1000, the decimal representation will terminate after 3 places. So over here as well it will terminate after 3 places of decimal. I hope this thing is clear to every student watching this video. Now you get a similar type of question over here. You see, this is the same concept is used over here. What is the number of trailing zeros in this question? Now what is the meaning of trailing zeros? First you understand that concept. It's a very simple thing. You have studied since childhood only. For example, I write 1500. Number of trailing zeros means the number of zeros at the end. So over here 2 trailing zeros are there. For example, you are writing 2000. So 3 trailing zeros are there. So we want to find over here, this question is very direct. Over here it is 12,000. So the number of trailing zeros is 3 only, right? You cannot do anything. Number of trailing zeros is 3 only. But every time you will not get a question like this, okay? For example, I am giving you a question. Suppose this is 2 cube and suppose this is 5 raised to the power 5 and this is 7 square and suppose this is 11 raised to the power 9. Okay. So if I write it as a number, are you understanding my question? If you multiply and write it as a number, then how many trailing zeros will you get at the end? That is the question. How many trailing zeros, how many zeros at the end you will get, like these numbers over here. So again you have to understand one concept. For example, if I am seeing this thing, this means it is 2 into 1000, guys. So it means it is 2 into 10 raised to the power 3. In the same manner, this number means it is 15 into 10 square. So what does it mean? That number of trailing zeros means that the maximum number of tens which you can form. For example, you see 10 cube is there, so 3 trailing zeros are there. Maximum I'm talking about. And over here 10 square is there, so 2 trailing zeros are there. So you have to decide that how many maximum tens you can form over here, right? So basically you see 2 cube is there and 5 raised to the power 5 is there. So can I not take 2 cube from here, and this is 5 raised to the power 5. So 1 5 raised to the power 3, we can use it. 5 square will be left as it is not required so as to make tens over here. So this thing is nothing but 2 into 5 raised to the power 3, or you can say 10 raised to the power 3. So maximum 3 tens we can form over here. It means 10 into 10 into 10. So you will say that this will terminate, or you can say the number of trailing zeros over here will be 3. I hope this logic is clear to every student over here. Okay, so let's move on. So you have got decimal representation of real numbers. We already have seen the decimal representation of rational numbers. Now we are talking about decimal representation of irrational numbers. So every time you will not get numbers whose decimal representation will terminate or non-terminate but repeat. There are numbers in which the decimal representation is neither terminating nor repeating. For example, I can take it like this. For example, 15.1, 2, 3, 5, 6, 8. So it is, you see, and so on. It is neither terminating nor repeating. It is not stopping after some places of decimal, and there is not a repeating string of numbers as well. So it is neither terminating nor repeating. So these type of numbers are known as irrational numbers. For example, square root of any non-perfect square number. Square root of any non-perfect square number will be an irrational number because they will have neither terminating nor repeating decimal representation. Now you will ask how you can show that the decimal representation of these numbers will be neither terminating nor repeating. For that you have studied the square root in grade 8. You might remember that, the long division method. So you can find the square root of 2 by the long division method. I'll not do it completely, but I'm just telling you. So you'll get 1 over here and then 2. Then you remember you put decimal, 2 zeros will come, and so on you can keep on doing. So you will get neither terminating nor repeating decimal representation over here. In the same manner, cube root of any non-perfect cube number is an irrational number. Cube root of any non-perfect cube number is an irrational number. So in the same manner, nth root of any number, which cannot be written as a power, as the nth power of a number, that is an irrational number only. For example, you see, cube root of 27 is not an irrational number. Simple logic is this will be 3. Why? Because 27 can be written as 3 raised to the power 3. 27 can be written as the third power of a number. So therefore, this is not an irrational number. For example, fourth root of 16 is not an irrational number. The simple logic is 16 can be written as 2 raised to the power 4. So 2 will come out of it, right? Therefore, this is not an irrational number. But for example, I take the fourth root of 18. This is an irrational number because 18 cannot be written as the fourth power of any number. I hope this thing is clear. Now there is one more example, pi. Pi is not an irrational number and pi is not equal to 22 upon 7 because 22 upon 7 is a rational number. An irrational number can never be equal to a rational number. 22 upon 7 is just an approximate value of pi for calculation purposes. Now other values of pi which you take for calculation purposes, 3.14, 3.143, these are just approximate values of pi for calculation purposes. Pi is not a rational number, it is an irrational number. So all the values which you take for calculation purposes, those are approximate values of pi. I hope it is clear to you. So that's all we needed to discuss in the decimal representation of rational and irrational numbers. Bye bye guys, take care everybody.